Okay, so we will continue our discussion on Gaussian elimination today, and actually with some applied problems. So last time we went over a method of how to solve systems by hand, and before we actually go and do how to program this method, what we're going to do today is actually we're going to go back to the original problem and say, well, how do I pose a problem in form of a system of linear equations? Okay? So we will actually see two examples today of problems that can be solved with Gaussian elimination. So let's get going with those. Let me open my device here. So let's look at this example, and this is a classical example from chemical engineering. Let's assume that we have 3 reactors. And the flow in between them is sketched like this. So this is my reactor number 1, reactor number 2. Or no, I'm going to put the 3 here, excuse me. And reactor number 2. So I have a flux going through pipes here, and input flux into reactor 1 is 100 meter cube per second. So those of you who haven't had transport phenomena yet or fluids, basically it's a volumetric flux per time, okay, that goes in through a pipe. And then some of the flux from reactor 1 goes into reactor 3. I'm going to call that Q13. I don't know what it is. I'm going to be looking for it. And the other part goes into reactor number 2. I'm going to call that Q12. Then from reactor number 2, what we have coming in is Q12. And what is coming out is Q21. And 21 essentially says that I'm going from 2 to 1. And Q23. And as far as number 3 goes, depending on what reactions I actually have happening in these, I have 2 batches coming from 1 and 2. And I also separately probably need some other fluid. And I'm going to say that 20 meter cube per second is simply coming in to 3 to get in whatever chemical we needed. And then finally the output is coming out, and it's called Q33. Whenever you have a system like this, if you are engineering it well, you want it to be at steady state. What does that mean? Everything is in balance, so whatever comes into the system per second also has to come out of the system per second. There is no accumulation unless you somehow are accounting for that accumulation as well. Okay? And that could be termed in your equation. So basically we want steady state flow through the system. So for this entire system, when I just look at the system, 1, 2, 3 together, what is the flux coming in? 120. So there's some of it coming into 1, some of it coming into 3, and what is coming out? So just based on that, what is Q33? Okay. So Q33 I immediately actually have, it's not really an unknown the way it was described here. So basically mass balance, what comes in equals to what comes out, and this is all done per second. For the entire system gives 100 plus 220 meter cube per second is equal to Q33. Okay. So Q33 is actually known. It's equal to 120. Okay. Now, my mass balance for steady state has to be true for the entire system, but also for every so-called node in this system where I have things coming in and out. Okay. So basically I will also go to my first reactor and do a mass balance, second reactor to do a mass balance, and the third reactor to do a mass balance. So this is something that you would commonly do. So if you have any flow of anything, you will do simply mass balance of fluxes. Okay. I could be also monitoring concentrations of things within these, so I would actually just have a slightly different calculation if I also had new concentration of the matter coming in. Then I might actually do a mass balance based on the those concentrations. Or second thing that you could also have that is similar to this problem, all of you are in statics or solids or both, okay? You could actually do force balances on various beams, and there you would basically do force balance of forces. So you would look at the force vectors, and at various joints you would balance them, okay? So there's various flavors of these problems, okay? Ultimately for steady, and you could also, of course, also have electrical current going on as well, okay? So in these types of networks, you are typically going to balance something out, and that results in a linear system of equations. One very simple equation that we got is already this one. It's a simple one, but it's still an equation basically in one of these unknown variables. Okay. So now we will basically, to get the others, you're going to do reactor 1. So what is the mass balance for reactor 1? What is coming in? I'm going to leave out the units. 100 plus Q21. What is coming out? Sure, we can do it that way. Minus Q12 minus Q13 is equal to 0. Reactor 1. Oh, it's not all projected for some reason. Okay, that is interesting. I don't know why. So this is, I'm going to write more in the middle. Is this better? There's like parts of the page, so I'm not projected. I don't know why. Okay. Now reactor 2, same thing. What is coming in? Q12. And then what is coming out? Q21. Q23. And then reactor 3, what do I have? Q23 plus 20 minus 120 equals to 0. Those are my equations, okay? Now I just have to rewrite them. Now, how many unknowns do I really have? I think it's actually easier if you want to call them x1. So this is the first one I counter. Or should I start numbering things from, so this is x1, x1, okay? Then the second one up is maybe x2. I'm going for like 1, 2, 1, 3. And then I'm going to change the color. Three. Okay. This is still x2. And Q23 is yellow x4. Does that make it easier to see which linear system I have? Okay. So basically, I could do this as a minus x1 minus x2 plus x3 equals to minus 100. x1 minus x3 minus x4 is a 0. And x2 plus x4 is equal to 100. Okay? So you can rewrite this. Will this system be fully determined? I have 3 equations. I have 4 unknowns. No. Actually, it turns out, so let's actually sum up. If I sum up first 2, okay, I'm going to have minus x2 minus x4 is minus 100, which is negative version of this. Okay? So it's actually only 2 equations here are independent. So I'm going to have 2 free parameters. And one can actually go and solve this with Gaussian elimination, just like we did last time. You will have one of the rows turn out all zeros, okay, as you go through the process. Or this is simple enough to just say, well, okay, let's call one of those parameters is x4, so x2 is simply x4, okay? And the second parameter is x3, so x1 is x3 plus x4, and then I just express also, and then I'm actually done. Okay. So we can actually solve this just by looking at the so can choose to solve, we can choose to solve by hand or by Gaussian elimination. But basically, if first, if 2 equations, or I'm just going to refer to them to as 1 and 2.
two are summed up, we will get an equation that is negative equation number 3. So it's not independent of them. So basically, which is minus x2 minus x4 is equal to minus 100. So that means that I have two equations for unknowns, two parameters can be chosen freely. And then the other two I compute based on the two that I chose. Okay. So say x3, x4. Then my solution is actually based on either this equation 3 tells me that x2 is equal to x4 minus x4 plus 100, right? I'm actually not looking at the equation from the previous page. And what is x1 based on the either equation 1 or 2? Can somebody tell me so I don't open?
Oh, wait, what?
So x3 is a free parameter. X1 is x3 plus x4 from number 2. And that's it. I can go back to whatever these were called as fluxes, Q1 to Q13. So this was Q12, this was Q13, this was Q23, and I think Q21 and Q23. Yeah, that's how I call it. So does that bother me in a system like this? That I have so many solutions and possibilities? That's actually a pretty well designed system. It has quite a bit of, like, you're not supposed to hit only one flux because there's somebody who is going to make sure that this experimentally works, right? And if you have one possible solution and you don't hit that one for some reason, that might actually cause trouble in the system. So this is just fine. So as long as you can control one or two fluxes in the system, then the others will just line themselves up based on your inputs into the system and outputs out. Okay? All right. So this is one of the systems with not a unique solution. Okay? And just I'm just going to put the side note. If we solved this via Gaussian elimination, one of the rows will turn to be all zeros. So this is rows. Grammar, but okay. Okay. All right, that is one example. So that's, again, mass balance or force balance. Those are common examples where linear systems show up. There's another one that is not necessarily all that obvious, and that is a model of a heated rod.
And this is another example of a linear system in applications. So assume I have a heated rod that goes in between two walls. So this wall is kept at temperature T0 is 40 degrees Celsius. And this one is kept at temperature 200 degrees. And I'm going to call it T5, and it's going to be obvious why in a second. So this is at my distance x, I'm going to call it x0 is 0. And this endpoint is at a distance 10 away. So the length of this is 10 meters, I believe. Okay. So these ends are held at constant temperature. And I'm wondering what is the distribution along this rod. And distribution would have been simple if I actually didn't lose some. So if I had a completely isolated system, I would give or take have a linear distribution in between. Okay, so I could just do a linear. But I'm losing some of the heat to the ambient temperature. My T ambient, TA is ambient. It's 20 C's. This is a rod, R-O-D, rod. So I have some heat transfer happening between the rod and the ambient. And basically how much heat I'm losing depends. There's a constant sort of transfer rate in between the two, but how much I'm actually losing depends on the difference between the temperature at a point and the ambient temperature. Okay? So that's what's throwing in unknown. So basically there's a heat equation for this system which says d squared t dx squared plus h. H is my transfer coefficient times ambient temperature minus T is equal to 0. So this is heat equation. If you haven't gotten this far in your differential equations, doesn't matter, we will solve it numerically. So the fact that you don't know how to analytically solve this doesn't matter. so you will find an alternative. Okay. And H again is the transfer coefficient between air, rod and air. So this is the actual rate of transfer that depends on the difference between the temperature. This is at a point and ambient. So this differential equation is true. I'm going to assume this is a one-dimensional problem. So my entire rod I'm collapsing to a point. So I really have like temperature is a temperature of X. So it's a function of distance. Okay. And again, this is a one-dimensional heat equation, as in I have only one spatial dimension. And I'm going to assume that I know what this heat transfer coefficient is. It's equal to 0.01 meter, and this is in meters. So this is 1/8
over meter squared.
All right.
So how do I solve for temperature numerically? Whenever we are doing numerical solution to a problem, I first have to define myself a grid of points where I'm solving the problem. I cannot solve problem continuously. That means that I would actually have an analytical expression for this temperature, and that's not something that I'm going after here. So first thing that you always do is you so-called discretize your space into a number of points where you're going to be looking solution for. And the finer the discretization, the more continuously it will look. Okay? But no matter what, if you're numerically solving for this problem, you're actually really just going to find a solution, approximate solution, and a number of discrete points. So first step is to discretize, and the way I'm going to do that, I'm going to say, okay, well, let's just add 4 points in between here. So I have one at the wall. So this is my x0 and x5, and I'm just going to do 4 points equally spaced in between. So that's essentially my line. So this is my x1, x2, x3, x4. If these are equally spaced, what is actual distance between x0 and x1? 2. So it's 10 meters total divided by 5 segments, right? So 2 meters, 4 meters, 6 meters, and 8 meters. And I'm really looking, what I'm looking for is temperatures T1, T2, T3, and T4. So my numerical solutions will simply find T1, T2, T3, T4 subject to this equation. Okay? That's how discretization of differential equations by and large works. Okay? So basically, we will look for T1, T2, T3, T4. And if you want to find more or a nicer solution, well, then you can discretize differently and actually put your spacing to be smaller, okay? And then you will be looking for T1, T2, T3, T4, T5, T6, T7, T8, T9, okay? 9. But you might already expect, since this is a linear system lecture, that we're going to get a linear system in T1, T2, T3, T4. Okay? So if you choose to have more points, you're going to have the size of the linear system that corresponds to this. So in this case, you're going to get a 4 by 4, but if you choose to have more points, you're going to have 9 by 9, or 18 by 18, or however many you decide to throw in between. Okay? So I'm going to stop here for today. We're going to continue next time. But essentially what we will do is we will approximate this derivative on this grid of points and basically set up our linear equation based on the discretized version of this equation. Well, yeah, but you can't have numerically